Hello, this is Nikita Daklukar, and this is my Lab 2, the magnetic field of a bar magnet. The purpose of this lab is to measure the magnetic field of a bar magnet, both on and off axis, by using a magnetometer on an iPhone, and we do this to find the relationship between the distance and the strength of a magnetic field. And to calculate all this, we're going to use concepts such as the Biot-Savart law and the magnetic dipole moment and dipole field formulas to find the relationship between strength and distance. And to give a brief summary of the results, we found that magnetic field and the distance are inversely related. As distance decreases, magnetic field increases. And at 45 degrees off axis, we found a magnitude of 9.5 teslas with a calculated N value of -2-ish and a dipole moment mu of 7.823 amperes per meter squared. So a couple of fundamental principles that we'll be using in this lab. First of all, the Biot-Savart law, which basically describes how the generated magnetic field is related to the magnitude, direction, length, and distance of an electric current generating that field. And in this case, we're going to treat the bar magnet as a loop of current. A formula for that is below. And related to that, like a specific version of the Biot-Savart law, is the dipole field formula, where we can calculate the magnetic field of a dipole off axis rather than on axis. And finally, we will be using the magnetic field and dipole moment for our ideas. Essentially, the magnitude of the torque of an object given in the magnetic field is the magnetic dipole moment, using perpendicular distance, of course. But the main main takeaway here is that this formula is distance dependent, that the magnetic field of the bar magnet is very much related to distance, also using two constants k and n, which we will soon calculate. So essentially, our experimental model is we were going to take the magnetometer app on the iPhone and then orient the iPhone so that the bar magnet's field is perpendicular to Earth's field. And this way we are aligned on true north, and we know that Earth's magnetic field won't throw off our measurements. So basically the sensor axis is north and the magnet is east and west, and then we record the maximum x component on the magnetic sphere on the magnetometer app at different positions relative to the iPhone via the bar magnet to find how the field strength changes with distance. The system is the magnetometer on the iPhone. The surroundings are the bar magnet specifically, but also the tape that we use to align everything, the kitchen counter, basically everything else around it. All the data we calculated at the different distances was then put into an Excel sheet to find the magnetic strength in teslas, and then plotted via the ln of the distance versus the ln of the magnetic field, Bx, specifically in the x direction. And then we found a slope of -2-ish, -2.0042, and this slope of the line is our n value. So now that we actually have our n value, we can then use some of the equations that we were given in the instruction packet to calculate the dipole moment mu. So first we use the equation ln of b of x is equal to ln of k plus n times ln of r of course being distance, n being the slope we calculated, and b of x being the magnetic field that we found using the using the measurements from the app and the Excel sheet. So plugging that all in, we end up with a k of 1.5-ish. And then now that we have the k in the end, we can solve for mu. We're given the equations b bar is equal to k times r to the n power, and b is equal to that whole mess right there. Basically, we just kind of set those equal to each other and then solve for mu, and I ended up getting 7.823 amperes per meter squared. And here we have our GlowScript code. So on the left, we can see all the coding that we did for finding the magnetic field at different points in relation to the magnetometer and the magnetic bar magnet. We have two locations that are on axis parallel, and we have two perpendicular ones, and then finally we have a position that is 45 degrees relative to the source of the magnetic field. So we get to see how the magnetic field behaves and interacts at many different locations in space around the magnet. Possible error sources were assuming that the only fields the magnetometer was picking up from was from the magnet and Earth, which again was canceled out because it was aligned. However, this is likely false because my experiment was on my kitchen counter, and we've got the microwave, the electric stove, all the different electronics that we have in our households that affect magnetic field. So what would happen if the magnetometer was not aligned with Earth's north? Well, then we would have to factor in Earth's magnetic field into our measurements, and it would throw everything off because we'd have two different sources of magnetic field. And finally, what if there were two magnets stuck end to end? Well, we've ended up with a magnitude twice as large calculated in our magnetic field, but the field would point in the same direction, so all the directions would be the same.